In this last probability video, we're going to take a look at how we can use what is called Bayes' formula to calculate some conditional probabilities. So we are solving probability problems with Bayes' formula. Formula is named after a great mathematician named Bayes, who did a lot of work with probability and statistics. We're just going to take a look not so much at the formula, but how the formula works, because the how it works is actually, I think, easier than actually using the formula. And basically the idea of what we're doing is we are finding the probability of A given B knowing the probability of B given A. So we're finding a conditional probability when we know the opposite condition. And so, kind of as an example to set this up, we're going to take a look at two jars. The first has 3 red and 4 green marbles. The second has 5 red and 2 green. A jar is chosen at random, then a marble is drawn. If the marble is green, what is the probability it came from jar 1? Well, let's take a look at kind of the tree diagram that models this situation. We could either come from jar 1 or jar 2, and we're going to say there's a 50-50 chance, a 1/2 probability that we went with jar 1, and a 1/2 probability that we go with jar 2. Then we could either end up with a red marble, or we could end up with a green marble. Now, from jar 1, there's 3 red out of 7 marbles total. And for green, then, there are 4 green out of 7 marbles total. In the other jar, we also could end up with a red marble or with a green marble. The reds, this time there are 5 reds in jar 2 out of the 7. And there are 2 greens out of the 7. We can then multiply down the branches to find the individual probabilities. The probability we get a red from jar 1 is 1/2 times 3/7. That's a bad 7. That's a 7 there. 1/2 times 3/7. And that's going to be 0.2143. To get a green out of jar 1, the probability is 1/2 times 4/7, and that's going to be 0.2857. A red out of jar 2, that's 1/2 times 5/7. That's going to be 0.3571. And finally, a green out of jar 2 is going to be 1/2 times 2/7, Whoops, my 3 up above looks really bad. There we go. Okay, 1/2 times 2/7, and that's going to be 0.1429. So now that I've got a tree diagram, we can actually calculate some probabilities here pretty quickly. We can find, for example, the probability of a green. Well, the probability of a green would be both of these green probabilities added together, 0.2857 plus 0.1429, and that would be, on the calculator, 0.4286. We could also calculate the probability that it is a green and it came from jar 1. That's right on our probability stem here. That's a 0.2857. So if what the question is asking for is the probability that it came from jar 1 given it's a green marble, we can put these pieces together because we know from our formula of conditional probability this is the probability that it came from jar 1 and it's green divided by the probability that it's green. And we just calculated both of those pieces. Jar 1 and green is 0.2857 over the probability of a green, that's 0.4286, and so we can divide. And when we divide that on our calculator, we end up with 0.6666. That means if we end up with a green marble, there's about a 2 in 3 chance, just a little bit short of that after rounding, 0.6666 chance that it actually came from jar 1. And that makes sense because there are a lot more marbles in jar 1. This is the idea behind what is called Bayes' theorem. I think I want to back up here. I had number 1 was the problem. My numbers are off, really minor detail, but that's my OCD for you. 2, 3, 4, this is number 5. Bayes' theorem. And Bayes' theorem is a way that we can calculate the probability of A given B. What we do is we look at the probability of A times the probability of B given A. That's what we did. Here, I'll highlight this in yellow just for the sake of pointing here. And that's what we did to find the green and jar 1. We multiplied the probability of the first part times the probability of the second part. That's what we did there. Then we divide by all the other probabilities that satisfy the condition. Essentially, we take the probability of A times the probability of B given A plus the probability of something else, maybe C, times the probability of B given C, plus the probability of D, plus the probability of E, plus the probability of F, times B given F, and so on and so forth. This down here, that's what we did when we calculated the probability of G. All the greens. We added all the greens together. So we said this is a green and that is a green. We had to add those together. And this is what we're going to do when we actually solve with Bayes' theorem. Instead of using this formula, which is a little bit involved, what we're going to do is we're going to make a tree diagram. And we're going to find in yellow here the branch that we are interested in. And then we divide by all the branches that match the given information, that match the green marble in this case. So let's try a few more examples. I have 2 more examples I want to run through to set up this idea of Bayes' theorem. in kind of some of the situations where you see it actually work out, a little more exciting than pulling marbles out of jars. One way is we want to know where our defective parts come from. Let's say a manufacturer gets 20% of its parts from company X. Which has a 4% defective rate. %30 of its parts come from company Y, which has a 3% defective rate. Finally, 50% of its parts come from company Z, which has a 1% defective rate. If a part is found to be defective, what is the probability it came from company Y? So we're asking the question, what is the probability it came from company Y, given that we know it is defective? I'll use D for defective. That's what we're looking for. Now the first question is, why don't they just get everything from company Z, which has a 1% defective rate? Well, it's possible the company Z cost more, and so they want to alleviate their cost. Maybe they did some type of simplex method problem, found out this was the distribution that gave them the most profit with the less expense. So now we want to figure out where this defective part came from. So there's 3 choices that have to be made. First, it could come from company X, it could come from company Y, or it could come from company Z. We are told X makes 20%, Y 30%, and Z 50%. So X is 20%, Y is 30%, and Z is 50%. Then, after that, the part either works or it's defective. It either works or it's defective. It either works or it's defective. And that's based on which company it came from. This is your conditional probability, the opposite direction. X has a 4% defective rate. So X 0.04 are defective, which means 0.96 work. Y? Y has a 3% defective rate. So Y 0.03 are defective, 0.97 work. And Z has a 1% defective rate, defective 0.01, so works 0.99. So we can calculate the individual probabilities by multiplying down the line. 0.2 times 0.96 on the calculator gives us 0.192. 0.2 times 0.04 gives us 0.008. 0.3 times 0.97 gives us 0.291. 0.3 times 0.03 gives us 0.009. 0.5 times 0.99 gives us 0.495, and 0.5 times 0.01 gives us 0.005. We're interested in the probability that it came from Y given it came from D. The branch we're interested in is it came from Y given it's defective. This is the branch we are most interested in. Now the given probability, the D that's given to us, we need to consider all the defectives. We don't care about when it works. So we've got a defective branch here, a defective branch here, and a defective branch here. The bottom halves are all defective. Those are the ones we care about. So to calculate the probability of Y, that it came from Y, given that it's defective, is equal to that interesting branch, the 0.009, divided by the sum of all of the defectives. 0.008 plus 0.009 plus 0.005. When you type this in the calculator to make sure the addition comes out right, make sure the denominator is in parentheses. So typing it in the calculator with the denominator in parentheses, I'm coming out with 0.4091 after rounding. The probability that it came from company Y is 0.4091. Almost a 2 in 5 chance that it came from company Y. That's how Bayes' theorem works. Very simple if we use the table, kind of weird if we use the equation, but the equation does all the exact same pieces in the exact same parts. Let's do one more example, make sure we're really good with Bayes' theorem. Kind of give you a life and death situation of Bayes' theorem. Let's say a test for a certain deadly disease. Yields a correct positive result (99% of the time). So if you have the disease, it will identify it correctly 99% of the time. It's very accurate. It also yields a correct negative result. (95% of the time). That means if you are healthy, 95% of the time it will agree you are healthy. What's interesting in the way they design medical tests is these two items are kind of in contradiction of each other. If you make it more correctly positive, you're more likely to get a false negative. So you gotta weigh one end or the other, and the medical profession and pretty much everyone else agrees that it's better to get a false positive than it is to get a false negative. A false negative means you have the disease and we don't know, you go away and you die. We don't want that. We want to know you have the disease. So we're going to err on the side of getting it correctly positive than correctly negative. So with these facts, it's also known that 2% of the population has the disease. It's spreading quickly. 2% of everyone has it. 1 out of every 50 people. So you decide you want to be preventative. You need to know, do you have to get your affairs in order? You go in, you get this test to see if you have the disease. if you get a positive result, what is the probability you have the disease? You got a positive result. Is the end near? What we're looking for is the probability that you have the disease given you've got this positive result. To begin with, you either have the disease or you are healthy. And we can assign those probabilities. The probability that you have the disease is 2% or 0.02. The probability that you're healthy is the opposite of that, which would be 0.98. Then they run the test, and you either get a positive test or a negative test. Positive test or the negative test. So we're told if the test yields a correct positive result 99% of the time. Correct positive result. That means you have the disease and you get a positive result. Disease, positive result, that's this top one 99% of the time, which means it's incorrect 1% of the time. We're told it yields a correct negative result 95% of the time, which means if you are healthy, you will get a correct negative result 95% of the time. So the opposite, 5% of the time, you might get a false positive. We can calculate all the individual results then. Have the disease, correct positive is 0.02 times 0.99. Let me try a different color here so I can be consistent. .02 times 0.99. That's a 0.0198. The false negative is 0.02 times 0.01, which is 0.0002. The healthy with a false positive, that's 0.98 times 0.05. That's going to be 0.049. I'll add a 0 just to make it consistent with the decimal points. Doesn't really need the extra 0. And the last one, 0.98 times 0.95. On the calculator gives us 0.931. Add a 0 to make it consistent. And now we've got all of our individual probabilities. We're interested in disease with a positive. Disease with a positive. That's the one that's most interesting to us. However, we have to compare it to our given information, all of the positives. So this top one is a positive, but there's also a positive result down here in the third entry. So to calculate the probability that you have the disease given a positive result would be that interesting result, the 0.0198, divided by the sum of the two positive results, 0.0198 plus 0.0490. Again, making sure that as you type it in the calculator, you put parentheses around the denominator. And when we type it in, we end up with 0.2878. Though you got a positive result, there's actually only a 28% chance that you actually have the disease. Now granted, this is significantly up from the 2% that you had in the general population. Now with a positive result, you're up to 28, almost 29%. So it's not looking great, but it's definitely not looking worse. Well, this makes people wonder if it's only going to give me a positive result correctly signifying the disease 28% of the time, is the test really worth it? Well, let's look at the opposite question. Let's look at the probability that you are healthy given you have a negative result. Did you get a correct negative as opposed to a false negative? Well, now I have to clear out my colors here because we're interested in different things now. Now we are most interested in being healthy with a negative result and comparing it with being healthy, just all the negative results. Negative and negative. So this gives me the 0.9310 over 0.0002 plus 0.9310. Again, remembering to put that denominator in parentheses. So we've got to put that in our calculator. And when we do, the probability that you are actually healthy when you get a negative result is 0.9998 when we round. Again, these two are always opposite each other. One can be really good, and one can be, well, there's a chance, but not a strong one. So the health community has decided it's better to get a false positive than it is to get a false negative. So if you get a positive result, there's only a 28% chance you actually have the disease. If you get a negative result, you are 99.98% sure that you are healthy. Remember, it used to be 98. Now you're up to 99.98. And this comes into play if any of you have had children. You probably had a test for various genetic disorders. And if the test comes back positive, it doesn't actually mean your child has the disease. It just means now the probability for autism has jumped from 8% to maybe 20%. And further testing is required. That first positive test, though, does not necessarily mean you have the disease, and Bayes' theorem explains why that is. Today's homework assignment takes a look at a lot of Bayes' theorem problems. Take a look at them, work them out, come to class with questions. We will see you tomorrow.